Okay, after talking about the barometer, we will talk about the manometer. Okay, the principle of manometry is based on the fact derived in the last session. That is, the height of a fluid column corresponds to a pressure difference. Okay, that's what we have said to be the pressure head. Okay, the pressure head. A manometer comprises a U-tube made of glass or plastic, in which containing one or more types of fluids, such as oil, water, mercury, etc. Okay, the fluids contacting with each other must be immiscible. Okay, if that's miscible, then that will be a very serious problem, as the fluid will be mixed together. Okay, we can see that the pressure measured by a simple manometer will be shown in this diagram. That would be a very simple manometer in this case. Due to the small density of gas, the pressure difference between the tank and position 1 can be taken as 0. Okay, we can neglect the pressure difference. And by Pascal's law, pressure in the fluid remains unchanged between 2 points in the same horizontal plane connected by the same fluid, so that the pressure at point 2 will be the same as set as point 1, so that you can jump from point 1 to point 2 directly if they are connected by the same fluid. Okay? As the fluid column at the right is exposed to the atmosphere, and the whole system is in static equilibrium, we can use what we have got before, that is P below equal to P above plus rho g delta z absolute, to determine the pressure at point 2. Okay? So that will be point 2 equal to PATM, okay, plus rho gh, so that you move downward to this position 2 from this free surface. Okay? Where rho is the density of fluid in the manometer tube. Okay? Well, similar to the barometer, although the height of differential fluid column is independent of the cross-sectional area of the tube diameter should not be too small. Otherwise, the capillary rise due to surface tension will be significant. Okay? So we would like to neglect this effect, so we need to have a sufficiently large tube to make this manometer. Okay? Well, in order to increase the precision of this manometer, an inclined manometer is made by using an inclined tube in the manometer design. The reason will be explained here. Okay? So let me draw that manometer out. So what exactly is an inclined manometer? Well, it's like this. Okay? So there's a tube. Okay? Okay? Well, that's a very simple schematic of an inclined tube. Well, you would like to measure the length of this fluid column. Suppose now the fluid column has got into this position. If we add a dotted line here, okay, so here we can measure the length. That is L, okay, that is L. That would be the length, okay. And here we would measure this angle. This angle is what? Is theta. Is theta, okay. And as we know that after we have inclined this tube to be the inclined manometer, actually the height would be unchanged. Okay, the height will be unchanged. So let us denote the height here. That will be h. Okay, so here by very simple trigonometry, we know that h is equal to L sine theta. Okay, so h is the opposite side of this hypotenuse. Okay, and because sine theta varies from 0 to 1 for acute angle theta, so it is more than or equal to L. Okay, because sine theta is more than or equal to 1. Okay. Because of this, that means L will be increased if an inclined manometer is used with h unchanged. So that because your measured value will be larger, the percentage error you got will be smaller. So the precision will be increased if you use the inclined manometer. Okay? Well, next we will talk about some more complex problems. Okay? Before talking about those problems, let us remind you something. Okay? For the complex problems, we can analyze them easily by using the following 3 facts. Okay? They have been derived before. Okay? The first one is that the pressure change of a fluid column is derived previously and is equal to delta P equal to rho gh. Okay? And the second one is that the pressure at a deeper position is higher, while the pressure at the top is smaller. Okay? These two facts can be summarized by a very simple formula that is here. That's a P below equal to P above plus rho G delta Z epsilon. Okay? The third thing is that if 2 points of same elevation are connected by a single type of fluid at rest, then they will have the same pressure. Okay? That's what we have talked about. That's Pascal's law. Okay? That's Pascal's law. Okay? The solving procedure is simple. Because fact 3 allows us to jump from one fluid column to the other, as long as along the way the 2 points are in the same continuous static fluid. Okay? Remember, it must be applied in a hydrostatic fluid. Okay? Therefore, in solving this kind of problems, we will select a point of interest or some points with known pressure and move towards our destination, which is another point of interest. Okay? By adding or subtracting rho GH according to fact 2. That means at a deeper position, you need to add them. Okay? If you go up to a high elevation, you need to subtract rho GH. Okay? I will use the following example to illustrate the idea.